So this is a title of a colloquium that's starting to get really old. I've been giving this colloquium since probably for 5 years. But I have some new results to report, so I decided I'd resurrect the colloquium. I used to call it the general case without a question mark. And when people saw that title, they thought I was either arrogant or vague or, well, they didn't know what to make of the title. So I put a question mark there to indicate that maybe it's a puzzling title for a talk. And I don't think I've given, I'm not sure any of you in this room have actually seen this talk, which is another good thing. Okay, so what does the general case in quotes refer to? It refers, first of all, to the following quote from an article by John Oxtoby and Stan Ulam that appeared in the Annals in 1941. I'll read you the quote, and then I hope to explain to you what it's about. They write that the conjecture has frequently been expressed, first by Birkhoff, then by Hopf and others, that ergodicity is probably the general case. The conjecture was never given a precise formulation, but it was based on the idea that a general transformation or flow should be expected to shuffle points in more or less random fashion, and therefore leave invariant as few sets as possible. So even if you don't know what the term ergodicity, that term means, I think it's clear what the point of this discussion is, that if you pick a dynamical system in some kind of random way or kind of general way, you should not expect to see really any invariant structures other than those that you kind of know about in the first place. So I'm going to, and in fact even Oxtoby and Ulam in their paper made precise what they meant by the general case. But I'm going to make it precise for you as well. I'm going to expand the context in which they discuss this problem. So the context of this talk is volume preserving systems. Okay, so this is a dynamical systems talk. We always consider, in the most classical forms of dynamical systems, we consider self-maps from a space to itself, a map from a space to itself, and we look at points in the space, and we apply the map over and over in a process called iteration, and we see what happens. Okay, well, the self-maps I consider are going to be defined on a set that has reasonable structure. So M will always denote a closed manifold. Put a Riemannian metric, it's a smooth manifold. Put a Riemannian metric on it. The metric itself is irrelevant up to, I want to use a metric, so put a metric on it, but it's irrelevant. But I want there to be a volume measure on this manifold. So I can either use a Riemannian metric to give it. I could use just a smooth top form to give a volume measure. Or if I have a symplectic manifold, and I will be talking about symplectic manifolds, I want my volume to be the one induced by the symplectic form. So non-degeneracy of such a form implies that if you wedge it with itself n times, you get a non-vanishing form. And I want that, the absolute value of that, to be the volume. Okay, and then the dynamical systems I'll consider are going to be at least homeomorphisms. So minimal regularity, I want to talk about homeomorphisms. But then I want to explore what happens if you make these into diffeomorphisms, or maybe even if you have that additional structure of a symplectic form, a symplectomorphism. So just a diffeomorphism that preserves that symplectic form. By the way, if you're not comfortable with symplectic, you can just think about volume. But we're going to see some slightly different things emerge when we consider these two different classes. And so the Fs that I will consider, these are Fs that are kind of natural with respect to ergodic theory with volume. So what that means is that I want to assume that F preserves volume. Now, since these are invertible, I can define it this way. Otherwise, I need to use a F inverse here to make sense of it. So what does it mean to preserve volume? It means if I take any set of positive volume, or even volume 0, and I evolve it by the dynamics, the volume doesn't change. So for example, the volume induced by a divergence the flow induced by a divergence-free vector field. For example, a symplectomorphism is always going to preserve the symplectic volume. And you can also have continuous volume-preserving maps, and even, well, not continuous ones, but we're really focused on the continuous ones here, at least. Okay, so this is kind of the general assumptions for any map I'm going to talk about in this talk. Okay, and so for these maps, for volume-preserving maps, there's a natural kind of basic question in dynamics you ask about such a volume-preserving map, and that is whether it is irreducible, right? So that's kind of the first question one asks about a dynamical system is there an invariant subsystem that I can study, to reduce the study to invariant subsystems? So ergodicity says that there's no invariant subsystems. So it's an irreducibility assumption. So the precise definition is simply that if I have an invariant set under the dynamics, a subset, it doesn't have to be smooth, just measurable, then it is trivial. Either its volume is 0 or its complement has volume 0. Okay, so that's ergodicity. It's a very simple notion. Here's an illustration. So suppose in M, I have some, well, this looks like an open set, but in general, I could have maybe an invariant Cantor set with positive volume. Well, actually, I can't. Ergodicity says that does not happen. Okay? So the question of ergodicity, well, it goes back to Boltzmann's work on ideal gases in the 1870s, I believe. And he didn't formulate ergodicity in these terms. He was interested in a sort of different formulation, what turns out to be a different formulation of ergodicity that was adapted to the problems he was interested in. And this is, to me, this should be the definition of ergodicity, and this is the theorem. Because here's the interesting property of ergodic systems. So what does this say? So if I have an ergodic system, or a system is ergodic, if and only if, when I take any measurable subset, and when I say measurable, I mean Borel measurable or measurable with respect to volume. Either way, you can state it either way. So if I take any Borel set, and I take almost any x, so with respect to volume, I just pick a point at random, and I apply the dynamics. So here's x, here's f of x, maybe f squared of x lands in here, f cubed of x, which is f of f squared of x, and so on. And I count for the first n iterates how many times the set A is visited. The proportion of visits in the first n iterates converges as n goes to infinity to the relative volume of A and M. So ergodicity, which is simple to define in these terms, actually has this beautiful interpretation that says that basically almost any point is equidistributed with respect to the volume. And in fact, when f is continuous, you can even make a stronger statement than this. But this is the theorem, the famous ergodic theorem, pointwise ergodic theorem of Birkhoff. Also, I believe, I'm told, independently proved by Karleman. This is the way I like to think of ergodicity. And in fact, this definition of ergodicity is actually, suppose you want to prove that a system is ergodic. You think, well, this is kind of the thing you would try to prove, but this is the much more useful formulation. Okay, so we start with a very simple example. So the simplest example, and this is kind of good because it's illustrative for what I'm going to say about the general case, is my manifold's a circle, so I'm in dimension 1. And there's really only one smooth volume on the circle, that's length. After a smooth change of coordinates, you might as well assume you have Lebesgue measure. Okay? So I consider Lebesgue measure on the circle, which I can think of as an additive group. And I consider a translation. So this is a circle with, let's say, circumference 1. And I'm just translating by alpha in the group, which is the same as rotating through angle 2 pi alpha, if you like, on the circle. And ergodicity, for such an example, well, it can be established using a simple argument with a trigonometric polynomials that goes back to Weil, or you can use Fourier series even. So to get a slightly weaker, there's actually a stronger statement than ergodicity for these translations. But in any case, F is ergodic, such a translation is ergodic if and only if alpha is not rational. Okay? So let's illustrate this. Let's see this picture. So unfortunately, this is a little bit faint, but here's the circle. Here's a set A. And I just want you to kind of be a little convinced by a fun little movie that if I pick a point at random and I translate through angle alpha, and if alpha is irrational, as it is in this case, the orbit of alpha will, over time, like evenly fill up the circle. And so I think it's easy to convince yourself that the proportion of time spent in this interval is proportional to the length of this integral, or actually is the length of this integral asymptotically. Versus the situation when alpha is rational. Well, if alpha is rational, then it's of the form p over q. And if I add p over q, q times, to a point x, right, it's like adding p, which is going back to where I start. So in this case, every orbit is actually finite. And in particular, for this A, you can see that actually none of the time as I go around is ever spent in this positive measure interval A. Now that's not quite a violation of ergodicity because this is a specific point. And ergodicity says almost every point will visit this set in the right proportion. But you can convince yourself if you move this point a little bit, I'm going to still avoid this set. So there's a positive measure set of points that avoid this set. So this is kind of the opposite of ergodicity. This is a periodicity, and this is ergodicity. All right. So that's my ergodicity illustration. And now let's go back to, just to remind you of what Oxtoby and Ulam were writing about. So let's consider the case of all rotations on the circle. And just think about it for a second. So you can topologize these by alpha, right? There's a natural way to consider the space of all rotations. And you can parameterize it by the circle itself. And if alpha is rational, then we're not ergodic. And if alpha is irrational, it's ergodic. So on the circle itself, ergodicity is really the general case. Because in any sense you want, the set of irrational numbers have volume, almost any sense you want. The set of irrational numbers have volume 1, or length Lebesgue measure. They're a dense G delta set, so they're large in the sense of the Baire category. And so that we could take as some kind of intuition, although it would be some kind of faulty intuition. Well, in some sense faulty, and in some sense a good intuition for what Oxtoby and Ulam are writing about here in the introduction to their paper. Okay, so maybe they're taking the circle as the model. Now I want to be a little more precise about what I'm going to mean by general in this talk. So we want to talk about, is ergodicity the general case? So I need to fix my universe of dynamical systems. And so there's several possible universes that are related to the question at hand. So I could look at the space of homeomorphisms, preserving the volume on M. Okay. So I can put on this the uniform topology. So the distance between two homeos is the distance, the sort of C0 distance, locally defined C0 distance between the diffeomorphisms and between their inverses. And in that metric, this becomes a complete metric space, and without the vol. But when you put the vol in, it's a closed subset of a complete metric space, and it is a complete metric space itself. Okay, so that's a topological space I might consider as my universe. So for example, on the circle, if I take homeo vol of the circle, this is equal to, or isomorphic to, the circle itself. You can check that. So it's just given by the amount you rotate by. And then I can, and I will do this, I can increase the differentiability of the systems in question. So I can look at diffeomorphisms, smooth maps with a smooth inverse, and use the CR topology to measure the distance between diffeomorphisms. And again, if I restrict to those that preserve volume, I still get a complete metric space. So I have a very nice topological space on which I can ask about sort of typical elements, just like you would ask about typical elements on the circle. And in fact, well, this is the same. Nothing really changes for the circle if you look at smooth maps or homeomorphisms. Okay, preserving volume is enough to give you a conjugate, some isomorphism with R mod C. And then we could look at symplectomorphisms, and again, put the CR topology. So these are three very natural classes of universes of dynamical systems in which we can ask, is ergodicity generic? And these last two, I just wanted to point out, we endow with this CR topology. Here we endow this with the uniform topology, so the C0 topology. And here R could range, I mean, it could also, for the purposes of this talk, R is going to range between 1 and infinity. And then what are some notions of general? So now I have a universe. And here's, at least topologically, the strongest sense in which something could be typical. Well, the strongest sense could be is it holds for all systems. Okay, so an example is Poincare recurrence holds for all systems. That's a pretty typical property. But a little bit weaker is the notion of being open and dense. So that's a really rather strong, to have a property be open and dense among all. I can't even think of a property that's open and dense among all elements of these, other than sort of trivial ones. But I can take properties that are open and dense, and if I take a countable intersection of open and dense sets, because I am in a complete metric space, I get I'm in a bare space. And so the resulting intersection is a dense set, and it's a very strong notion of density. So it's it's called generic. It's a residual set, or the property is called generic, and you can't have a generic property and its complement, a property and its complement both be generic. So it's sort of like full measure, but it's topological. So the rational numbers are generic. They're residual. They're countable intersection. They're also full measure. Notice I haven't said anything about measure, like measure 1 property. That's because these spaces, except for the circle, are infinite dimensional spaces. They're not even locally compact. There's no, there's no way to put a fully supported probability measure in particular on these spaces. Or even a fully supported locally finite measure. I mean, probability doesn't work. Now, there are some other notions of typical in these universes, but they involve things like looking at, finite dimensional families inside. So anyway, these are the two notions I'm going to talk about. And going back to the Oxtoby-Ulam paper, here was kind of the landscape. Here's what was known about ergodicity back then. So there was Boltzmann who hypothesized that ergodicity should hold for his idealized gas systems. And here's a picture of a Sinai billiard, which is a idealization of Boltzmann's system. So this is an example of a system that was hypothesized to be ergodic by Boltzmann. But he put it in very vague terms. Weil, so a lot of this, by the way, a lot of this discussion has a home here at IAS. A lot of these people worked here, were specifically brought here and nurtured here to work on these types of questions. So there's a certain kind of appropriateness. But I'm so bad with names and with history, I'm not going to even attempt it because I haven't prepared. Okay, but Weil, and I'm staying on his street here, he studied equidistribution properties of numbers in the circle. Those generated by dynamical systems and some that aren't. But the systems he considered were quite rigid. They're like rotations. He was able to show, for example, that rotations on the irrational rotations on the circle, irrational rotations on tori, these very special rigid systems had this ergodic property. And then that was earlier, and in the 1930s, Birkhoff and von Neumann actually formulated the definition of ergodicity, the kind of modern definition that implies the equidistribution of orbits. This in a functional analytic L2 sense, and this on pointwise, looking at orbits of points. And then there were these very interesting models. So Hopf and Hedlund, kind of working separately, both proved that in some sense, a large class, or a very interesting class of geometric systems have this property of ergodicity. And so Hopf in particular showed that if I take any compact surface with negative curvature, for example, a hyperbolic surface, then the geodesic flow, which is a dynamical system on the unit tangent bundle, is ergodic. I won't say much more about this example, but these were basically the only known examples at the time. And this was extremely rigid in the sense that it takes place on the torus or something like a torus. And these were very special as well. The manifolds themselves, well, on the one hand, the ergodicity, the mechanism, and I'll mention this again later, the mechanism for ergodicity of these examples is very robust. But on the other hand, the kind of class of examples themselves and the manifolds they live on is very special. So at this time, it was really open whether every manifold emits an ergodic transformation, volume-preserving transformation. So this was the question that drew in, perhaps posed to them by Birkhoff, which drew in Oxtoby and Ulam. And they answered this question in this paper. So if I take any compact manifold, there is a ergodic volume-preserving homeomorphism on that manifold. So topology is no obstruction to ergodicity. Okay? Now, this joke is becoming old at this point, but when you want to construct something in dynamics, you have kind of several options. One is to build it with your bare hands, and the other is to build it with your bare hands, meaning the bare category theorem. And this was, in fact, how they made these constructions. Whoops. Got to get this in the right. So in fact, what they showed is that ergodicity is generic among homeomorphisms. And so in fact, the general homeomorphism preserving volume, I don't need the plus. I don't know why I put that, except I guess I need the plus. No, I don't think I need the plus. In fact, it should be expected to shuffle around points in a more or less random fashion. So I want to say just a word about the technique in the Oxtoby-Ulam theorem. So they were, in a sense, very much motivated by this example of rotations on a circle. So here is what an Oxtoby-Ulam map, one of these homeomorphisms, kind of looks like. These ergodic homeomorphisms. So your manifold, up to some identifications which have volume 0, is just a cube. And then you can break it into little cubes, all of the same volume. And if I have any volume-preserving homeomorphism, there's a way to kind of, each cube kind of is going to go to an intersection of other cubes of positive volume. But since the volumes are the same, you can actually apply a marriage lemma type argument to kind of get a matching between cubes and their images. And then by perturbing inside of volume preserving transformations that aren't continuous, you can produce something ergodic, and then there's a Baire argument and a Lucen type approximation argument that gives you homeomorphisms. And so kind of what these things look like is you just put all the cubes and they kind of rearrange. But what's really happening is basically this cube is going to this, is going to this. There's some permutation of cubes using, using this kind of marriage lemma argument. There's a permutation of cubes. And then you come back and you do something ergodic. And there's always, you can make something ergodic in a cube. It's pretty simple, in a single cube. All right. So, so these are typical in some sense. But even Oxaby and Ulam recognize that these, and I had a quote, but I think I lost it, that these systems are in no way really typical of the kinds of systems considered in the kind of field where this originated, which was Hamiltonian dynamics. Okay, they're the kind of maps that are considered preserve a symplectic structure, right? So they have to be smooth, at the very least. Okay, so in fact, as it turns out, the lack of smoothness in the Oxaby-Ulam construction is actually a pretty, it's a pretty key feature of their argument, because the general case doesn't hold when you look at C infinity diffeomorphisms of a manifold. Either, yes?
So their argument is not constructive, right?
No, that's right.
Is there any constructive version of that proof?
I don't think so, no. Yep. In fact, while this argument is constructive, none of the arguments today I will give you are constructive. They're all going to be Baire type of arguments. Yeah. So fast forward another, 13 years. I can't do math. Fast forward, and this is from the ICM address, the translation of the ICM address of Kolmogorov. And it is the case that people were thinking pretty hard about whether, when you look at volume-preserving systems or symplectomorphisms or Hamiltonian systems, whether ergodicity would be the general case. And Kolmogorov showed that if you, now I have to kind of translate this for you a little bit, that if you work in the analytic category, just at the opposite end, that in fact ergodicity is not the general case. I mean, there's many other consequences of this theory that he developed, but that is one of them. So I will read the quote. Are dynamical systems on compact manifolds, generally speaking, ergodic? And should we consider a continuous spectrum as the general case and a discrete spectrum as the exceptional case? That's another question I won't explain. In the application to analytic canonical systems, this is Hamiltonian systems, like the type arising from mechanics, the answer to both questions is negative. Okay. And so why is ergodicity not the general case? So this is, this is known as the modern subject of KAM theory, developed by Kolmogorov initially with some examples in the analytic setting, and then Arnold in the C infinity setting, and Moser and others bringing the smoothness down to a minimal amount of smoothness later on. What does it say on a surface, for example? So on a surface, being symplectic and preserving area are the same thing. And what the KM theory shows is that ergodicity, as I've said about 3 times now, is not a dense property, not even dense. Forget about residual among C3 area-preserving diffeomorphisms. And they isolated a mechanism on the surface to block ergodicity. What's the mechanism? Well, you just need a fixed point or a periodic point. And when you normalize it, it should be elliptic. So it should have a normalization where in a neighborhood of that periodic point you see up to a C3 expansion, you see twisting. So you have invariant circles and you see twisting around that periodic point. That is a C3 open condition, and when you have that, the map and any perturbation is going to have a positive area family of circles. And that is going to block ergodicity for many reasons. One is that it's positive area, but it's not everything. So it's invariant. Another is that in the case of here in the case of a surface, these things have codimension 1. So they actually separate the manifold into many, many invariant components. Okay, so, and in fact, this can be generalized to higher dimensions, both for symplectic morphisms and for volume-preserving diffeomorphisms. So, yes?
In these topologies, is ergodicity automatically a G-delta property?
Ergodicity is a G-delta property.
Density question.
So in this case, it's a density question. That's right. There's higher properties that are not, yeah, that's a good question, that are not G-delta or known to be G-delta. But okay. So it's not dense. So yes, it is a density question. And this was first done in the symplectic setting, but more like in the 90s, there were some generalizations. So basically, whenever you have here an invariant family of tori with a certain twist family, a twist condition, and these would be half the dimension of the manifold. Or here you can do it codimension 1. These will persist under appropriate conditions, twist-like conditions. These will persist under perturbations and block ergodicity. Yeah. Okay, so let me just summarize in the context of the general case, what is the role of smoothness? So in our CR universe, consisting of homeomorphisms, diffeomorphisms, or symplectomorphisms, if we go between r equals 0 and r equals infinity, I can describe to you the two extremes. So when r equals 0, ergodicity is generic, but it's ergodicity of this very special kind that you can approximate arbitrarily well by what almost looks like a periodic transformation. Okay? And so, in fact, the same argument that gives you density of genericity of ergodicity actually gives you density of non-ergodicity. Okay? So it's very, very much like this situation over here, where the rationals are dense and the irrationals are, of course, generic. On the other hand, if we go to over to, I keep doing backwards. On the other hand, if we go to r equals infinity, ergodicity is not dense because of Km. And in fact, and I won't really discuss this in this talk, but ergodicity can be robust. So non-ergodicity is not dense. It can have interior. Ergodicity can have interior. Okay. So now in dynamics, and apparently in symplectic topology and other areas as well, it's very interesting, actually, to, well, I mean, it's interesting and sometimes it's boring, right? So every C1 manifold is a C infinity manifold. That's kind of boring, right? But sometimes varying differentiability, very interesting things can happen, and especially when you look at dynamics or geometry or things like this. So there are some interesting geometry questions of a similar nature. Starting at r equals infinity, you can ask the same question for any r. And of course, the CR topology, it's a funny thing if you're looking at generic properties. Because in the CR topology, if I compare the CR to, say, the CR minus 1, it's harder to prove things are dense, but it's easier to prove things are open. So we have like a whole world of possible generic properties that are sort of completely incompatible as you vary R. But a lot of properties, as it turns out in smooth dynamics that I study, what holds for infinity, you can actually bring the regularity down to 1 plus epsilon. Now some things you can only go down, as I said, like Km, you can only go down to a finite thing before something else happens. But a lot of things you can go down to 1 plus epsilon. Then you see a huge break in behavior at C1. And then, well, then you have to ask what you mean by going below. There's lots of different ways. But even C1 and Lipschitz are kind of very different animals. OK, so as I just wanted to point out, that there's some. It's interesting to kind of see. Well, it's a big unknown land. OK, and knowing kind of what properties kind of persist under perturbation, it kind of gives you a kind of sense, a feel of the features of the CR topology on one of these universes. Okay. So in the case of intermediate differentiability, we look at this question. The KAM method fails for like C2. It just, even if you have a twist condition, you can kill the twist, and then you won't have this KM phenomenon. Oxaby-Ulam technique, I will explain to you in a minute, is going to fail when you have any differentiability. So the conclusions of the Oxaby-Ulam theorem, the kind of approximations you get using this approximation by periodic systems, it doesn't hold for C1 diffeomorphisms. That's going to be kind of the point of this talk, the rest of this talk. And whether ergodicity is a generic property is an open question for R, like R equals 2. And any manifold, it's completely open. For R equals 1, it's still an open question. So in this talk, I will focus on the case of C1 diffeomorphisms. So I'm going to be working with the C1 topology. The C1 topology, so if we were looking at Hamiltonian systems, although I'm not explicitly talking about Hamiltonian systems, that would be the C2 topology on the Hamiltonians. A C1 topology is a very interesting topology because we understand dynamical systems reasonably well from a C1 perspective, C1 generic. I mean, there's still lots of interesting open questions. But the C1 topology is a very interesting, it has two really important features. So one is that a C1 diffeomorphism, if you look locally, it looks linear. So that's what sets it apart from, say, Lipschitz, by Lipschitz homeomorphisms. So, and we know linear algebra, or at least now I think the undergrads at University of Chicago do, but like 5 years ago, no. OK, we know linear algebra. And the second, and this is a really important one, is that C1 perturbations can be localized. So if I have an orbit and I want to change something right here, I can, and I have a specific change I want to make, I can renormalize a fixed perturbation and make it arbitrarily small and stay small in the C1 topology. Whereas, so just a little exercise, if I take R times phi of x over R, where R is less than 1, and I differentiate this once with respect to x, I get phi prime of x over R. And so the C1 size, the C0 size can go to 0, and the C1 size stays fixed. But if I differentiate this one more time, if I let the C0 size go to 0, I try to localize, the C2 size blows up. Okay? So this here, this baby here, gives you some local control. Now, it's a combinatorial question. It's a lot. There's a lot of questions about how you put together localized perturbations. But the analysis of C1 diffeomorphisms is a combination of linear algebra and a certain amount of combinatorial analysis and some topology. So we're going to focus on this case. And in this case, I told you that Oxaby-Ulam fails. And that's because there's an obstruction to applying their technique of approximation. And that's entropy. Okay. So entropy, well, I think probably a lot of you have seen entropy in various contexts. And there's different kinds of entropies. There's entropy from physics. We're not going to talk about that. But even just for a map from a space to itself, there's a notion of topological entropy. That's not what I'm talking about. What I'm talking about is entropy of the transformation with respect to the invariant volume. And so I'm not going to define entropy, what the entropy is. And I'm only going to say in words what it means to be entropy 0 for a general map, like a homeomorphism. So, but this is, I think, kind of the best sentence you could use to describe it. So I start with my manifold, and I partition it in a measurable way into finitely many sets. And I can use that to code my orbits of my system by finitely many symbols. And I can take my invariant measure, and I can push it forward to my symbol space. And then I can look at the kind of information that each iterate, well, I can iterate a lot of times, and I can ask how much information that gives me. So if I know, for example, what all the symbols are up to time n, like what is the measure of the set of all points that have the same trajectory, the same symbol? I have to take the log, which is a measure of information, and then I average that. And I look at how that grows as n goes to infinity. And presumably, as the things get smaller, that should grow at some rate. The identity, it won't grow at all. But in any case, if it grows at some exponential rate, then it has positive entropy for some partition. Otherwise, it has entropy 0. So for example, for a rotation on the circle, you can imagine, say, partitioning it into 2 halves and just rotating those 2 halves and kind of looking at the number of names you can get. Well, there, it doesn't, an upper bound for the entropy in this case. This has topological entropy 0. In fact, the number of even elements in the partition is growing only linearly. So that's definitely entropy 0. OK, so rotation-like systems, where things just kind of bop around for a while, and then they come back close to themselves and bop around, those have entropy 0. Now, for a diffeomorphism, I can give you, it's a theorem. This is an inequality of Ruel. But here actually is a precise definition of what it means to be entropy 0. For a diffeomorphism, entropy 0 is equivalent to saying if I take a point at random and I look at the growth of the derivative, the norm of the derivative, it's 0. It's sub-exponential. So vectors can grow in length or shrink in length, but not in an exponential way. OK, so this is entropy 0. And I have the following kind of meta proposition, which is if this approximation by periodic things, as in Oxtoby Ulam, can be applied, so if it holds in some class of volume-preserving systems, then in fact 0 entropy is generic in that class. So as a consequence, if I look at homeos preserving volume, the general one has entropy 0. On the other hand, this is definitely not the case for C1, or at least on certain manifolds. In general, this does not hold in either of these spaces. So let me give you examples. Okay. So, well, I'm just going to put down some words. So what I just said is that for some manifolds, entropy 0 is not even dense among the C1 systems. And that's not in here, nor in symplectomorphisms. So what are the systems that I have in mind? Well, there's the Anosov systems. So if I have a diffeomorphism of a manifold that's C1, we say it's Anosov. If the tangent bundle to the manifold splits into 2 invariant subbundles, so preserved by the derivative. So a vector in this bundle goes to a vector in this bundle. A vector in this goes into the vector of this. The vectors in here are uniformly expanded. With respect to some Riemannian metric. There's a metric-free way of defining this as well. And these are uniformly contracted. This property of being Anosov, and I'll give you an example. This is a C1 open property. If I have an Anosov diffeomorphism and I perturb it, it's Anosov. And it also has positive entropy. any C1 anossive diffeomorphism has positive entropy. Okay? Now, what's the catch? Conjecturally, there aren't very many anossive diffeomorphisms. Conjecturally, they're all conjugate. After a relabeling of orbits, they're linear automorphisms of tori, or nil manifolds. Okay, a larger, in fact, a significantly larger class are the partially hyperbolic diffeomorphisms. So such an F is partially hyperbolic if the tangent bundle to M splits into 3 subbundles. This is for center. This is expanded. This is contracted. And then this is what's called dominated. So vectors in this bundle can be expanded or contracted. So this is the expansion seen in this bundle is not as strong as the expansion in this bundle, and the contraction is not as sharp as the contraction here. This is also C1 open and also has positive entropy, these systems. And I'll explain in a minute why I discuss both examples. And these systems, there are restrictions of some restrictions known for what manifolds these can live on. But this gives a very rich class of systems by contrast. Okay, so there's partially hyperbolic. And then there's basically any map that has a bundle that's invariant with a complement that dominates it, and in which you see expansion or contraction or even something weaker has positive entropy, and it's persistent. So it's these invariant continuous subbundles that lead to persistence of entropy, positive entropy. So to give you the simplest example, here's the so-called cat map. Here's an anossive diffeomorphism. So I take a matrix with entries in determinant 1. Such a matrix acts linearly on R2. It preserves the integer points. And so it induces a map on R2 mod Z2, which is T2, the 2 torus, which is depicted by a square by this fundamental domain over here. And this particular map I've chosen, well, it's symmetric, that's just nice. But it has 2 eigenvalues. It's determinant 1. And it has 2 eigenvalues, one bigger than 1 and one less than 1. Now, let's watch what this induced map does to the 2 torus. And you'll see that, linear maps, again, undergrads, right? They take squares to parallelograms. So here's the image in R2, and we can overlay some fundamental domains for the original torus, and then kind of reassemble these pieces. And we see kind of what this map, which is not homotopic to the identity, so it's a little maybe harder to imagine, but you can see here what this map does. This is the expanding eigendirection. This is the contracting eigendirection for that matrix. And you can even see in one iterate that this direction has been stretched out by the eigenvalue, and this has been contracted. And so I have a field of directions on this very simple example. And the field of expanded eigendirections is E+, and the field of contracted is E-. And this has positive entropy, and if I perturb it a little bit, it continues. Okay? So this cannot be approximated. Okay, because information, so I didn't quite say this, but if you think about it, at least for the linear map, it's a nice exercise to kind of see what happens if you try to code orbits in this system. And you can see that these kind of average information that's generated grows exponentially. And in fact, it's the log of, in this particular example, it's the log of the expanding eigenvalue. On the other hand, so I won't go too much longer. On the other hand, so I just said, we can't use Oxtoby-Ulam for maps with positive entropy. So are they ergodic? So there's a funny thing. So there's this kind of shuffling around form of ergodicity. And then I mentioned what Hopf and Hedlund were doing back in the 30s. They were looking at systems that kind of had this Nossoff type property, in fact. And they were proving by very different mechanism that these systems are ergodic. So on the other hand, C2 systems that are a Nossoff in preserved volume are always ergodic. And so it implies that generically, among the C1, either, and this is true for symplectomorphisms and diffeomorphisms, you need an approximation. You need something a little extra. But ergodicity is a bare property, as someone mentioned. And so it's possible, using density of C2 and C1, to show that, in fact, these systems are generically ergodic. Okay, so if you have this tons and tons of structure, if you have a continuous splitting of the bundle, where you have expanded and contracted, think about it for just 1 second. On dimension 2, this can only happen on the 2 torus, because the Euler characteristic has to be 0. Okay, but if you have this, you have ergodicity. Partially hyperbolic diffeomorphisms as well are generically ergodic. This one follows from, in this case, it follows from what I'm about to tell you. And in this case, this is an earlier work with Avila and Boki. So at least I can end on these 2 results. I think I've maybe given you some things to think about. So this is the older result with Avila and Crozier. So C1 generically in diff vol. I wish this were aligned, but it's not. Positive entropy implies ergodicity. So in exactly the complement of where you might hope to apply the Oxtoby-Ulam techniques, you get ergodicity. And a couple comments about this. So it's not just ergodicity that's implied. C1 generically, if you have positive entropy, which means there's some positive volume set on which the norm of the derivative grows exponentially. That's basically what positive entropy means. If you have that, then because the C1 topology has this mix of kind of flexibility and control, you can show, I mean, there's a certain rigidity, but there's flexibility to it. You can show that actually there's a continuous way to split the bundle where instead of vectors in here being uniformly expanded, we have that for almost every point, vectors in here are non-uniformly expanded in the sense of Lyapunov exponents, positive exponents. And similarly, non-uniform contraction. And this is as strong as you can say. This is the strongest result. You cannot conclude an Nossoff because there are open sets of positive entropy. For example, partially hyperbolic, but there are others that are ergodic. Okay? And then the second implication, is the more recent work. Now what I want to, this is my last or second to last slide, but one thing I want to remark is this statement is completely false for symplectomorphisms. Because this result says that you can make all vectors be expanded or contracted. You can split expansion and contraction into 2 different bundles that are invariant. Symplectomorphisms can have a bundle here, and do, that is neither expanded nor contracted, or no, sorry, that is neither expanded nor contracted, so maybe there's some ellipticity going on. And when you try to perturb, the expansion and contraction, they mix up with each other inside of this bundle. The ellipticity is robust, and you can't split away expansion and contraction. So this is a false result for symplectomorphisms, but here's what's true for symplectomorphisms. So generically for symplectomorphisms, positive entropy actually implies partial hyperbolicity. So you have this continuous splitting with uniform expansion and uniform contraction. And by the earlier work with Avila and Boki, that implies ergodicity generically. All right. so I don't want to go over. I just want to say there's a little bit of history. Ricardo Magnier, in his 1983 ICM address, he sort of proposed that one take, and this reminds me very much of what Simeon Philip, sorry, I didn't mean to focus on you so intensely right there, but some kinds of things that he's been doing as well, but from a very different perspective. But in any case, whenever you have a volume-preserving map, you have a measurable splitting that looks something like this. And Magnier proposed that in the C1 topology, because of its kind of flexibility, special features of the C1 topology, one could sort of break into two situations. Kind of one, you could take all these, you can take all the exponents and make them 0, okay, which is 0 entropy. And the other is you can make a perturbation and you can introduce a splitting. So he proposed some kind of approach like this, and he announced some results without proof. One of his results is basically the dimension 2 version of the two results I've announced, and that was proved by, based on some notes of Magnier, that was finally proved by Boki in 2002. So it's a bit non-trivial. But you get this entropy 0 and ergodicity, and in this case, non-uniformly a Nossoff in dimension 2 implies a Nossoff. So Hanna Rodriguez-Ertz did the case for volume preserving in 3 dimensions. And just a comment, if we just look at density of orbits instead of ergodicity, that property is generic on all manifolds in the C1 topology. Okay, and then I'm just going to end on a question, which is, what about the initial question of Oxby and Ulam? Can a generalized, so it's a question I think Katak posed, can one apply a generalized Oxby-Ulam argument in a C1 generic way, somehow, to get ergodicity for entropy 0 systems? That seems like a very hard question, as is all questions involving 0 entropy, as far as I can tell. Okay, but I mean, it's a bit enticing, because we've removed at least one obstruction. And note, if yes, you can do that, then ergodicity is a generic property in diff 1 vol. So that's all I have to say. Thank you
Very much.